Welcome, Business Calculus students, to the first of several videos in our final exam review. You can go ahead and print your final exam review worksheet from Blackboard and work through these problems with me. Now, as you saw from your midterm exam, the midterm problems were very similar to those on the midterm review worksheet. The final will be the same way. The nature of problems that you see in this final review worksheet will be the same nature of problems you can expect on the final exam. Remember, the final exam is comprehensive. It covers everything from all semester, starting with limits. There will be fewer problems on the actual exam than on this review. But if you feel comfortable with these problems, that means you are prepared and ready to take that very important final exam. So let's get started. In this video, I'm simply going to work through problems 1 through 4, limits and average rate of change. Problem 1 is asking us to find the limit, and if you'll remember, your first attempt in calculating a limit is always to plug in that target value. But if we plug 3 specifically into the denominator in this case, we're going to get a 0 in the denominator, and that prevents us from calculating the limit. So instead of direct substitution, we have to apply an algebraic technique to rewrite the expression first before we evaluate the limit. So on the first problem, notice we can factor both the numerator and the denominator. The numerator factors as x plus 7 times x minus 3. The denominator is the difference of two squares, so it factors as x plus 3 times x minus 3. Notice in the factored form, we have a common factor in the numerator and the denominator, which we can cancel. Also observe, that was the factor causing the problem. If I plug 3 into this factor, that's where I'm going to get the 0. But now that we've canceled or removed that factor, we'll be able to evaluate the remaining limit by direct substitution. Notice if I plug 3 into the denominator now, it's non-zero, so I'll be able to actually calculate my limit. When we evaluate the limit, we drop the limit operator and simply plug in our number. So we have 3 plus 7 on top, 3 plus 3 on the bottom. That gives us 10 over 6, and 10 over 6 reduces to 5 over 3. So the limit there is 5 over 3. All right, we're off to a good start. Not too bad. Remember, if you can't evaluate your limit first by direct substitution, try to factor and cancel. We'll run into the same problem on number 2. If I attempt to evaluate by direct substitution, that means I plug in my target value, specifically in the denominator. Notice it gives me a 0 in the denominator, so I cannot evaluate the limit directly. I have to rewrite the expression or manipulate it algebraically first. In this case, I'm not going to factor it as we did in problem 1. Instead, I'm going to make use of the radical that happens to be in the numerator. We can rationalize either the numerator or denominator to attempt to calculate the limit. So in this case, we will rationalize the numerator. So I'm going to multiply the top and the bottom by the conjugate of that numerator. That means I'm going to use the same two terms, but a different sign in between. So we'll multiply the top and the bottom by the square root of x plus 4. I'm going to add some parentheses here to kind of guide our thinking. That indicates that we should FOIL. So in the numerator, if we go ahead and FOIL these two binomials, the product of the first two terms, square root of x times square root of x, gives us x. Notice the outside terms would be positive 4 square root of x. The inside terms would be negative 4 square root of x, and those two terms would cancel. They will always cancel when I'm using conjugates. Then we'll multiply our last two terms. Negative 4 times positive 4 gives me negative 16. Now, in the denominator, I'm going to refrain from FOILing. I'm going to leave those in factored form and I hope you can see why, because notice we can now cancel the trouble factor, the one that was causing the 0 in the denominator. The remaining expression, then, we can evaluate the limit by direct substitution. Remember, when we evaluate the limit, we drop the limit operator. So I'm plugging in 16 for x and simply calculating the result. So the correct limit on this one is 1/8. So remember, if you run into that impasse where you have a 0 in the denominator, try those algebraic techniques. Factor and cancel, or if a radical is present, rationalize either the numerator or the denominator, wherever your radical happens to be. Problem number 3 is, notice a limit at infinity. We have 3 rules for calculating limits at infinity. You can either memorize the rules, or you can calculate it algebraically by dividing all the terms by the highest power of x in the denominator. I'm going to show you the algebraic calculation first, and then I'll remind you of those 3 shortcut rules. So what we're going to do is find the highest power of x in the denominator, which happens to be, in this case, x to the power of 1. Then I'm going to divide all the terms in the entire expression by x. Then simplify. Remember, carry your limit operator until you actually evaluate that limit. 5x over x reduces to 5. 3x over x reduces to 3, and then 7 over x will not reduce. If we evaluate the limit of the top and the bottom individually, we'll find first we have a constant in the numerator. The limit of a constant is always a constant. So the value of the limit of the top is 5. In the denominator, we have the limit of a constant. Again, the limit of a constant is a constant. But notice that second term. As x approaches infinity, that means as the denominator grows without bounds, this fraction crashes down to 0. So as x approaches infinity, this term heads to 0. So now we can simply see the value of the limit is 5 over 3 minus 0, or 5/3. All right, so if you don't have those 3 rules memorized, this technique will always allow you to calculate the limit. So let me remind you what the shortcut rules are if you're willing to memorize them. We have 3 cases, and we observe the degrees of the numerator and denominator to decide which rule to use. If the degree of the numerator is less than the degree of the denominator, the limit is automatically 0. In this case, if the degree of the numerator is equal to the degree of the denominator, then the limit is the ratio of leading coefficients. And that's what we came up with on this one. The last case, if the degree of the numerator is greater than the degree of the denominator, then the limit will either be positive or negative infinity, depending on the signs that you have. Okay, so it's a good thing to go back and review those 3 shortcut rules, or simply remember this algebraic technique. Problem number 4 takes us into average rate of change. Remember, you have 2 rates of change that you've studied in this class: the average rate of change and the instantaneous rate of change. The instantaneous rate of change, remember, is related to a derivative. The average rate of change, however, is simply a slope. Specifically, it's the slope of a secant line on a curve. If you'll remember, the formula for average rate of change is f of b minus f of a divided by b minus a. Now look at that formula. It looks just like slope. In algebra, you probably learned the slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. This is the same thing. We have the difference in the y values divided by the difference in the x values. So ultimately, we're just calculating a slope. So let's identify a and b. The first value given is a, the second value given is b, and our function, f of x, is this root function. So we need to calculate f of 8 minus f of 5 divided by 8 minus 5. So to evaluate f of 8, we simply find the function f, and we plug in 8. We know our function f is given over here, so I'm going to plug 8 in for x. I end up with 3 times 8 plus 1 over a radical. Next, I'm going to subtract f of 5. So I'm going to go to my function this time and plug in 5 for x. We have 3 times 5 plus 1 under the square root. In the denominator, we have 8 minus 5. We can go ahead and calculate that as 3. We're almost there. We just have a little arithmetic to do. So let's evaluate these radicands. On the first one, I have 3 times 8, which is 24, plus 1. We have square root of 25. In the second one, we have 3 times 5, which is 15, plus 1. That gives us 16. We have the square root of 16, all divided by 3. Evaluating those roots, we have 5 minus 4 over 3, or simplifying, we end up with a rate of change of 1/3. All right, thanks for listening. Take a little break. Come back in the next video. We will start derivatives using rules of differentiation. I hope that looking back over this, you may be a little bit rusty, but I hope it comes back to you pretty quickly.